My name is Alex Sutton. I'm a program manager in the Azure Specialized Compute team. So I work in the compute infrastructure. I'm responsible, or I work on our AI and HPC infrastructure and some of the compute services that we build to make doing deep learning, AI, machine learning at scale easier in Azure. I've got a really fun job. We get to play with the latest technology, figure out what processors, GPUs, other accelerators might make sense for our customers, work on the system design. We tend to think balanced system, CPU, memory, disk, but also absolute performance where it makes sense, and then cost. We also get to do things at scale, lots and lots of VMs, lots of data, try and break things so we can find any of the issues and bottlenecks and problems before you do. And then we get to work with really interesting customers with fun, challenging problems that push the limits of what we do on Azure. Some of those customers are internal teams developing our own AI algorithms and services. We do a lot of work with external customers too, particularly around new services, new GPUs, or just people with really fun, interesting challenges. Well, what I'm going to do today is talk to you about a couple of the patterns for using GPUs and AI at scale in Azure, thinking about how do I run a single job across multiple GPUs, how do I scale out many jobs to many nodes, and then how do I do other parallel scenarios. First, just a view of how we think about these services from a platform point of view. So you have your application, your pipeline, your AI that you want to go and run in Azure. We have a wide range of CPUs, GPUs, FPGA now that is providing the compute infrastructure. On top of that are virtual machines or virtual machine scale sets for operating at scale. You can come in at this level. You're responsible for everything, the VM, the drivers. We do make it easy for things like the data science VM that has the Tesla drivers there, the NVIDIA stack, and a number of deep learning tools. People who come in at this level are kind of thinking lift and shift. Let me move an existing infrastructure into the cloud, or they're specifically designing multi-cloud tools where that's important to them, and they're handling the abstraction to run across different infrastructure providers. Next level up is taking advantage of one of our paths or platform services. It could be Databricks for processing your data, Batch AI that's providing a compute cluster in the cloud, or Azure Kubernetes service if you're working with microservices. All of these are being used today by customers with AI and machine learning workloads. There's no one better than the other. It really depends on what's your favorite tool set, what makes sense for your application or pipeline. We're making sure that all of these work very well both at scale and with the compute fabric that we have on Azure. The idea here from an AI perspective is you submit the jobs, we take care of the infrastructure for you. Then above that is Azure Machine Learning. That's providing a tool set for team data science, experiment management, hyperparameter tuning, things that you would have to otherwise build and deploy on your own. We think there's a lot of value there. There's other tools as well that may build on our paths. And what's key is you have the choice of working at whatever level of the infrastructure makes sense from you. You can think of this almost as IaaS, PaaS, and SaaS. Think about what intersection is going to work best for you. I'm going to focus mostly today on GPUs and Batch AI and how we provide that at scale for training and inference. So the first scenario is scaling up a training job for a single job across multiple GPUs. You want to go faster. You may have a lot of data that you need to train. You may be building larger and larger models too big to fit on a single GPU, or a combination of the two. So you need to have your AI model work with a lot of data and many GPUs. There's two main patterns for this. First is data parallel. I have a lot of data to train. I'm going to run an instance of the model on every GPU and pass a subset of the data. You synchronize after each pass through a mini batch, figure out what the next parameters are, and continue the training. There's a lot of optimizations here in terms of, are you running the training synchronously across all of the nodes, asynchronously, different ways of optimizing what I'm passing in terms of the data for each node and the gradient descent. This is very, very common by customers who want to speed up image training. If I have millions and millions of images to train, it makes sense to spread my model out across multiple GPUs and speed it up. While it does sound great, there are issues. You may need to change your script to be aware of the multiple machines. How do I communicate the synchronization after each batch? The frameworks make it easier, but it's not as simple as saying run this job on one machine or run it on 4. The second scenario is model parallel. I have a model that's too large to fit on the GPU memory in machine, so I want to say put different layers on each of the machine, and then communicate as I go step by step to different layers in the model. So here I'm using the same training data, but I'm doing different layers on the GPUs. This could be on 2 or 4 GPUs in a single box, or tens to hundreds of GPUs in a cluster. Here you have more synchronization, because I'm synchronizing the inputs and the outputs from each layer to the next. This is really more an advanced scenario. It's not common in all models. We see it on Microsoft a lot by the speech team, by natural language processing. The speech team has run models up to over 1,000 GPUs at supercomputer centers. They're running in tens to hundreds of GPUs in Azure now. It takes a little bit more smarts. You need to think about how I'm designing the network, where am I placing the layers, really thinking about the communication and how I'm going to scale. Is it layer to layer on a single GPU, on the box, or across a box? You do need to think about bottlenecks here. If I'm communicating across multi GPUs on a single box, the PCI bus becomes an issue. This is one of the reasons why we deploy only 4 GPUs for our mainline NC series VMs. You also have to think about the file system and how I'm feeding data to the VMs. The training rate of images per second can get high. So we have a number of recommendations of different types of storage that you can use. We see good performance with Azure Blob and Blob Fuse. Sometimes an NFS server makes more sense. In other cases, I need to deploy a parallel file system. Multi-node, so I'm communicating over the network, either the Azure front-end network or InfiniBand. Is a little bit more challenging. Not every framework supports multi-node training or multi-node training well. Not every framework can take advantage of the InfiniBand network that we have in Azure. InfiniBand is important because it provides higher bandwidth and lower latency than we have on the normal Azure network. The accelerated network, what we're seeing, is doing pretty good, but for the very large models, we really take advantage of InfiniBand. And again, here the file system can become a bottleneck. So a couple of examples of speed up. We published a tutorial earlier in the year from the AI for Earth team showing a image classification model. They showed good speed up from 1 to 64 GPUs, fairly linear. They were able to see some benefit in training up to 148, but the performance started to fall off. This was more of an experiment for them, so they didn't invest a lot in the performance optimization. We have this code up on GitHub, so you can try it out. This is actually an example of, we did the training over the front-end network. You could use the 1-bit stochastic gradient descent and CNTK to reduce the data from node to node. You can do tweaking of the mini batch size. Operating at the scale does require effort to get the maximum of performance, but we're excited to see that you got pretty good scaling up to a large number of GPUs. The second is a benchmark from NVIDIA that they published for the first DGX1 that shows good scaling to 8 GPUs on a single box. In this case, they're doing the GPU to GPU communication over NVLink, not over the PCIe bus. So this is one way that NVIDIA is helping people scale to larger models. And I have a little bit more to talk about this approach a little bit later. So I'd like to bring up Ian Finder from our GPU team to give us a demo of distributed training.
So, as Alex talked about, distributed training can be a little bit intimidating at first. There's a bunch of different frameworks out there for training your models. Not all of them support multi-node configurations. We have, on the NC series GPU SKUs that we launched at Supercompute last year, InfiniBand. And we've been getting a lot of questions about using that for training models. A lot of customers want to train quickly. A lot of customers want to train cheaply. What I've put together here is a little bit of a demo where we're going to run through the normal TensorFlow Inception v3 benchmark, but we're going to do it on 8 GPUs spanned across 2 of our Volta 100 nodes. And then we're going to do it again on 32 GPUs spanned across, again, our new Volta 100 nodes. The cool thing is this demo is all built around standard open source stuff. We're using the stock TensorFlow container from Docker Hub. We're using the normal Horovod distribution from GitHub. We have some scripts to put all this together. We're using the standard canonical Ubuntu image. And then we're using Jupyter with our Azure Batch Python SDK to tie this all together. This is something any of you can do. It's up on GitHub, and it's really quite quick. So in this Jupyter notebook, I'm going to walk through setting up the job. First, we have a little file that we read that contains our Azure Batch configuration. This is your subscription ID, the storage account you want to use, et cetera. We'll read that in now. I'm going to reevaluate that cell. There we go. And then we have our training data set. Now, one of the big things about using Batch is part of the value prop of Batch is you're not paying for IaaS resources when you're not using them. You want to only pay for these expensive GPU SKUs when you're doing training. You don't want to keep your models, your files, your data there. So we've made it really easy with Batch to connect to Azure Blob Storage. So you can host your data set there, your outputs there, and using our Batch SDK, really easily set up the parameters of your job to read from that storage, to write to that storage, et cetera. So I'm going to set up the file share here. And this will all be up on GitHub later for you guys to run yourselves. Oh, yeah. There we go. And you can see here we've picked our NC24RS SKU. That's the 4 Volta 100s in a box with InfiniBand. The cluster is actually already created. I'm just going to kick off the training job here. So again, I configure the output directories, configure the job, and sorry about that. That's embarrassing. I forgot to evaluate one of the cells. Okay. Now we're ready to submit our job. So the main purpose of this is just to show you that we actually are submitting the job here on stage. We didn't have this canned. It's coming in live with all the mistakes one could make in a live demo. And So that's our big job. That's with 32 GPUs. And now we have another demo here with 8. We'll do exactly the same thing. And once I submit the job, I'm going to flip over to the batch portal and show you guys what's actually going on under the covers. All right, great. So in my Jupyter notebook here, I'm going to call a feature of the batch SDK that'll allow me to stream the output of the batch job. And when we come back here in a moment, we'll actually have the results of our training job sitting right here in this Jupyter notebook. And again, this is all, nothing custom to Azure. This is all built on really, really easy to deploy open source stuff. I'm going to flip over to the Azure portal. And in here, you can see the resource group that I'm using for this demonstration. Here's our small cluster, our large cluster, and our jobs. 2 of these jobs were ones I ran right before coming here, and 2 are the ones we're running on stage. The output in the Jupyter notebook is going to be the jobs we're running right now. Now, batch lets you do some really interesting things. You might think it's less cost-effective to use, say, 4 GPU-equipped nodes than 1. But with a lot of these training jobs that are embarrassingly parallelizable, you will actually get linear speedups, which means your job will complete 4 times quicker if you're using 4 times as many nodes. So you're actually saving money or paying the same amount of money and getting your results faster. For these clusters, we can configure auto-scaling so that when you're not submitting a job, you won't pay for the resources that you're consuming. That's a really powerful feature. Historically, batch tasks have been a little difficult to debug because you're using a kind of asynchronous deployment. But what we also have built in batch is the ability to SSH to any of your nodes through a single endpoint. So if I pull up this nodes definition here, you'll see a bunch of different ports, and these are all natted to my different cluster nodes. So if there's a problem, you can simply log in, pull the logs off of the node, and of course we collect STD out and STD error right here in the batch portal where you can see it. You can also take a look at the other resources that your job is using. If I go into any of these. And you can see the STD out, STD error listed here. So right now we're waiting for job pickup. And while we do that, I'm going to actually flip over and show you the results of the benchmark from a previous run. So this is my earlier job. And you can see here we've actually completed it. And here are all the files involved with that. STD error, STD out. Take a look at STD out here, and I can actually get the results of my benchmark. So this is on the group of 2 nodes, 8 GPUs. We can do 1,500 images a second. It's taking a little longer than I'd hoped for job pickup, and we're kind of on a schedule here. So I'll tell you the outcome of the other one. It's 5,500 images per second. So with only about a 10% parallelization penalty, you can get much better outcomes. It's roughly the same cost to do this training job in parallel and get the result 4 times faster as it is to wait around. I guess with that said, I will turn this back over to Alex.
All right, thanks. Thank you, Ian. So what I really like there is if I had a training job that took four hours to run because of the amount of data I was training with, and I could scale it up to four times the number of GPUs, I can get that job done in about an hour for about the same cost. And it's really not as much about cost, but about the productivity of your data scientist or researchers that can do that many more runs if they're experimenting or still playing with the model, or if you either have deadlines or a lot of models to train. What's powering this is the family of GPUs that we have available in Azure. We have 3 types of GPUs. First is the one optimized for graphics, the NV series. This uses the NVIDIA M60. We ship it with the Quadro driver for high-end workstation apps, or the Grid driver more for a VDI. We actually have a lot of people using this for training too. They believe it's faster for their work. Also, if you saw the AirSim demo down on the exhibit floor, it's a autonomous driving simulator that does it by replaying video scenes for the car's sensors to a view. They do that with the NV series. All of these are available with 1, 2, or 4 GPUs. The NC series is our compute GPU. It's the NC V1 uses the Kepler series from NVIDIA, the K80. NC V2, the Pascal P100. NC V3 is the latest with Volta. All of these are available with 1, 2, or 4 GPUs. So you can get an NC6, an NC12, or an NC24. Those are the number of CPU cores that come with it. So you're either getting a single GPU, 2 GPUs, half the box, or the full box. The NC series also has a second backend network, the InfiniBand network that we use for the multi-GPU training. You'll notice, as well as we moved to the V2 and V3 series, we introduced premium storage and moved to the Broadwell chip. One thing that we do have to improve the PCI performance is dual root, not single root. And finally, we have the ND series, which is optimized for deep learning. This is using the NVIDIA P40 GPU. The compute series supports double precision floating point, very important for engineering, HPC simulations, financial services. The ND series is single precision. The most important part, though, is it supports 24 gigs of memory. So it's very useful for people that have large models or lots of data to train. People are using it both for training and for inference. Here, there's no right answer. You need to figure out what's going to give the best performance for your model, which is going to be the best price or best price performance for what you need, as well as regional availability and just availability of cores. We're constantly adding more GPU clusters around the world based upon demand. They tend to sell out pretty quickly, though. I'm excited that we're introducing 2 new families later this year. First is a rev of the NV series. Based upon customer need in the VDI and kind of engineering workstation space, we're updating to a newer CPU and doubling the amount of memory and local SSD. That's really more for a desktop type scenarios. But I'm very excited that we'll be introducing V2 of the ND series. This is the 8 GPU, 8 V100. This is basically the equivalent of the NVIDIA DGX2 box. So if you're doing a multi-GPU training, you've now got the ability to scale to 8 GPUs on a single box with the low latency communication over NVLink. We've also updating the CPU to Skylake, increasing the RAM and local SSD based upon customer asks around the processing that they're still doing on the CPU to prepare the data to feed those GPUs. In many cases, it makes more sense to copy the training data locally so I can stream it fast to the GPUs. The second scenario I want to talk about is now scaling out. If the first was how do I scale up one model onto multiple GPUs, now how do I scale out training with multiple jobs? Multiple jobs onto multiple GPUs. This is really important in terms of experimentation. A lot of deep learning is still kind of a black art and playing around with different algorithms, different networks, different parameters. There's a lot of iteration as I'm trying things out, or I want to try things out at scale. I may do a brute force hyperparameter study. I may use some of the experimentation tools. I may use hyperdrive in Azure Machine Learning to go and run hundreds or thousands of jobs for me and tell me what the optimal configuration is. It's really the more I can do, the more I can get better results, you don't have to limit yourself to scale. In these kind of the CPU world and more of the machine learning actuarial space, we have people regularly running at tens, hundreds of thousands of cores on Azure. The idea of a 150,000 core job doesn't scare us. We actually have customers doing that several times a month. So when we're thinking about scale of running on a few or tens or hundreds of GPUs, fine. And thinking about people that are running at scale today, we can handle several orders of magnitude higher. The problem is the infrastructure can get in your way. I need to have a cluster. I have to provision those machines with the GPUs. I have to make sure the right drivers are there, the right software. I have to set it up for both batch and interactive use. People do like SSHing to those machines and running things interactively until they figure it out. Then they'll go and run at scale. When I'm working with a cluster, I need to queue work. It may be one user running a bunch of experiments. It may be a team sharing a set of VMs. So I need to prioritize jobs. In the case of the multi-node, I need to start that MPI job, gang schedule, and make sure that I'm doing the MPI run properly. We make that easy for the frameworks, or you can create your own. Then, of course, I need to be able to monitor it, handle failures. If a machine dies, can I go in and restart that node? Again, you need to think about data. How do I scale that? Scale the access to the training data to those tens or hundreds of machines? How do I gather all of the output logs and models? And how do we do it in a secure and a compliant way? This has been a requirement at Microsoft for a while. If you think about how our internal teams are training with data, a lot of customers are asking as well for what they call eyes-off training. How can the data scientists submit a job, see the result, but not have access to the data on the box? Someone cares about cost. Scaling up is great, but I need to scale down as well. I need some sense of governance and what I'm going to pay. I also want to take advantage of the different pricing models on Azure. You can use the GPUs on a demand. If you're willing to make a 1 or 3 year commitment, you can get a 40 to 60% discount and priority or guaranteed access to those machines. Or on the other side, you can take advantage of low priority VMs, which is Microsoft's equivalent of spot pricing. If we have the VMs available, you can get a 70% discount. Very, very useful if you're learning, if you're starting out, if you're experimenting, or you say, hey, if I can get access to these machines at this really low price, I'll do twice as much experimentation. And then how do we integrate this into your workflow? One of the things we really think about kind of at the platform level of how do I build this into kind of industrial style training? How do I do a repeatable batch style scoring? How do I go and do my training every day, every night? And how do I integrate with a wide range of tools? So what we have is a service called Azure Batch AI. It's built on our low-level batch service that's designed for developers. This is providing a data scientist-tuned experience for doing deep learning and AI and ML training in the cloud. It's designed to make it easy to leverage a cluster of GPUs, a cluster of CPUs, and run a bunch of stuff in parallel to save you time. You can use it with Azure Machine Learning later in the year, or with your own pipeline and tools. Ian showed you one view of it. Let me show you another demo. So one of the things that people really like doing is the idea of experiments, a parameter sweep in the HPC role. So what I want to show you now is running 9 different frameworks for a Cypher 10 model. So I want to go and do image training, but I don't know what algorithm I want to use, or I want to see how do they all work, how are they different, which one performs more. So I've got a cluster of 10 GPUs that I've got set up. I'll run through this notebook, which is available on a GitHub. Cluster is already there. Should already be there. changing the network. Okay, cluster. Okay, so you see I've got a cluster with a 10 VMs. I can go and see details. This is similar to what you could get from the CLI. You can see a table of a status. This shows all of the properties that are configured with the cluster. You know, the size, NC6 using a dedicated and the file system mount that I have. Let me now go and submit the jobs. So I'm going to submit jobs for 9 deep learning frameworks and run 10 epochs each. There we go. So CNDK, Chainer, MXNet. Keras, we'll go take a quick look at the portal. Are they starting to show up? Okay, they're starting. You see, as soon as they're submitted to Batch AI, they start to run. It's in the cluster. I've got 5 of them going now. Let's see if they're starting to run. So this is sending the output from NVIDIA SMI to a web service and database that we have, and we're doing the visualization here. This is just an example of you can use open source tools to do your monitoring. It's useful to see what percentage of the GPU is being used, how much memory is being used. The ones on the bottom, TensorFlow by default tries to grab all of the memory on the GPU, so it's really high, and some of the other frameworks are a bit lower. I can go, this is using the API, but I can see the list of jobs that are running. Let's try it from here as well. Let's see, Batch AI, job list. So there I can see the 9 jobs. They're running on my NC6 cluster, all running. What this job is doing is actually running each job in a Jupyter notebook. So it's designed to help you see how each of the frameworks are going. It goes and starts the notebook on the machine, writes the output to the notebook on a file share, so you see all of the results when it's done. As Ian showed, I can see the standard out from the job. So let's go and look at the TensorFlow job. I see it's about through 5 of the 10 epochs. If I go to the portal, I can go to the same thing. I can see the details for the job. I can go look at standard out. So I'm still through 5 epochs. I can do this from the command line tool to see what VMs is this job running on, which is their nodes. And then if I need to SSH to it. One word on quota. The default quota for anyone working with GPUs in Azure is 24 cores or 4 GPUs. If you need additional quota, additional machines to use with Batch AI, you can create a support request from the portal. create an issue type of quota. Say that you're using with batch AI, and then in the next step, say what you're looking for. I need so many cores of NC6 or NCV or NCV3. This will go to the support team, the capacity management team, and we will fulfill that quota request. Let's just check how the TensorFlow job is running. Job is done. So I can go through and download the notebook. So you can see there's the job is done. You can save the notebook locally. Realized I need to start Jupyter. And we will just there you go. See, so you can see the results that we were streaming out, all of the epochs, total training time 166, and the error rate. And one of these notebooks was created for each of the frameworks and stored back on the file share. Just a little bit more about batch AI. The main concept is a job. This is the work that you want to get done. It's the number of resources that you need, the number of VMs, the number of threads to start, and then the configuration for the framework that you want to use. We have schema for the most popular frameworks. You say, here's how many TensorFlow workers, parameter servers that I want. We go and start the job. We make sure that we collect standard out, standard error, map directories for the logs and the models. You can submit thousands of jobs in parallel. We know how to start the multi-node or single node job. In order to help scale, we're introducing a new API in the next month or so, and we're adding containers on top of jobs. First is the notion of an experiment. It's a group of jobs. This could be a hyperparameter sweep. It could be a day. It could be a model. It could be a team. You can then go and query on that group. You can filter. You can rerun failed jobs. There's no limit of the number of jobs or number of experiments that you have. Above that is a workspace. It's a container for a set of experiments. We view this as a long-lived resource. It could be a project. It could be a team. It could be a dev or test environment. This is an ARM resource in Azure. We need something at the root in ARM to contain everything. There is a limit of the number of ARM objects. We think having 800 workspaces is good. There's an unlimited number of experiments and jobs. You can have scale for whatever you need and keep those around as long as you like. It's pretty straightforward to create a job. Here's a snippet of the command line at the top where I'm saying create a job in the East US data center, name of demo job, in the demo group, resource group on the demo cluster, and then have the configuration for the job in this JSON file. Down at the bottom is a snippet for running a TensorFlow job. I'm running on a single node. This is the path to the script using one of the environment variables that we created. Then where do you want the standard out and standard error to go? We have samples to get you started. In our team's GitHub site are recipes for using all of the popular frameworks, as well as doing hyperparameter sweeps and batch scoring. We have Python scripts. We have command line. We have notebooks, single GPU, multi GPU, and distributed. Feel free to leave us comments or feedback there. We have people submitting pull requests. We welcome your ideas or any help. Cluster is what you're running on. It's the resources that you are using for running the jobs. You have a single type of VM per a single type of VM family per cluster, an NC6 or an NC12. You specify the VM image that you want. It could be a base image, and then I'll use containers. It could be the data science VM or your own. They can use standard or low priority VMs, and you can do manual scaling or auto scaling. The auto scaling is great, so you don't leave a cluster running over the weekend. Clusters are also rooted in ARM, so we have our basic RBAC roles, who's allowed to edit the cluster, who's allowed to submit jobs. Most people, however, are using a base VM and having all of their training library and code in containers. You can bring your own container or pull it from a public registry. We have examples of how to leverage the NVIDIA DGX registry, including if you want to store your secrets in Azure Key Vault, because you have to log into NVIDIA in order to pull down their containers. If you're pulling a container from Docker Hub, we do recommend for kind of enterprise use, you copy it to an Azure container registry for performance and reliability. If you're using a container, batch then handles the directory mapping, mounting volumes, setting it up for you to SSH in or run the multi-node jobs. We have flexible ways of using storage based upon the amount of data that you have, how complex an environment that you want to use. We started out with Azure Files. It's a great way to get started, but you will hit scalability limits. We're recommending now that people start with Azure Blob Fuse. It's a POSIX, almost POSIX compliant layer on top of containers. It effectively gives you an NFS-like experience on top of blobs, and we're seeing very good performance there. Beyond that, Batch AI can set up a managed NFS server for you. So if you need a lot of data in Stripe disks, we can set that up. Beyond that, you can use one of our scripts to set up a parallel file system, Lustre, Gluster, or others. We will be investigating the Azure product, a company that Microsoft acquired a couple of months ago that provides a nice memory and SSD cache in front of storage. The main lesson here is you do need to test your workflows, figure out if Fuse is good, if you need NFS, or if you need a parallel file system. We're building a great experience with Azure Machine Learning as a front end for Batch AI. You'll be able to create clusters and submit jobs with the Python SDK, manage Batch as a compute target for training or scoring, or you can bring your own cluster. This is really exciting for solutions like Hyperdrive that provide hyperparameter tuning and optimization as a service. You can also go and then submit jobs if you're using the Visual Studio tools for AI or in a VS Code, be able to connect directly to a Batch AI cluster. Azure Machine Learning helps you complete the loop. I can then have a trained model with Batch AI, deploy it to a container that I can then use as a web service, deploy to an FPGA, or use for scoring in Batch. Here's a snippet of using Batch AI from the Azure ML Python SDK that will be coming later in the year. Up at the top is how I'm provisioning a cluster, setting up a cluster of NC12SV3, the Voltas, using low priority because I want to go and do some experimentation if the VMs are there, and I'll deploy a cluster of 4 with auto scaling. Then down at the bottom is how easy it is to submit a TensorFlow job with the SDK to Batch. And then just a screenshot of submitting a job from Visual Studio Tools for AI. On the left, you can see the clusters and job, and then there's a nice dialog box for configuring the jobs. So you've got the ability to work with Batch AI from ARM if you're doing automation. We have Portal for monitoring of full CLI and configuration files for managing clusters, managing jobs. An SDK for integration. If you're working in Python, in Java, or C#, we're open to other languages as well. We have a number of people using the Java SDK in particular to integrate with their enterprise workflows. And finally, we have support for Azure App Insights. If you want to collect CPU counters, the NVIDIA GPU counters, like what I showed with Grafana, you can go and pipe those to App Insights. We also have some samples of how do I use Batch AI with Azure Functions or Azure Scheduler to kick off jobs. Say I want to go and run a nightly training or scoring job, and then working with Azure Data Factory of how do I stage and prepare data for a job. To talk about how they're building on Batch AI, I'm excited to invite our partners Wei Zhang from VIP.com and Xin Zhang from KaiCloud.
Thank you, Alex. Hello, everyone. My name is Zhong Wei. I work in the VIP.com. I'm a general manager in charge of overseas export business. So great honor to be here to share the innovation we achieved in the last months. So VIP.com is the Chinese biggest flash shopping platform and the third largest e-commerce platform in China. And we are producing 300 million active users per month and $20 billion USD for 1 year as revenue. So we supply the fashion and beauty, and I think the ladies love us so much. So as the next future 5 years, VIP.com regard the expansion of overseas business as a core strategy. So, but different with Alibaba and Jingdong, we define ourselves to restructure our product through the way by the technology driven. So we use the AI as a core of the platform, which is a better way to match, the goods, the services, and the customer needs. For example, we give the customers the favorite reading content and information to help them to make it better for shopping decisions in different scenarios. So also we've faced the biggest challenge for us. I think first is we need the very strong and super fast processing capability of basic data, such as for 1 million of new product pictures need to quickly form the label through the AI machine and recommend to the users through the algorithm. And all these works can be done in the minutes level. The second, we need to get AI to quickly to learn the country's consumers' behavior, such as holiday customers' reading performance and others. And we require the training of the modeling algorithm must be shortened from 2 months and to 1 week. So the modeling can be copied to another country, and our business can be extended to other country. And finally, I think the platform and the human resources, the cost can be managed and controlled. We are the small team and with a limited budget. So we need a framework to manage the overall works, like the data processing, the modeling, tuning, A/B testing. So all the works can be integrated and operated by the team and the platform. So at the time that we want to find the most cost-effective way at last. So I think we can achieve these impossible goals well through the Azure platform and the partners. So I want to invite Zhang Xin from our partners, the CEO of KaiCloud, to introduce you more for the details.
All right, thank you. So, okay, so press here. All right, so to achieve the business ambition of VIP.com, so we actually need to overcome some technical challenges, right? So those are very unique. For example, the solution has to be highly adaptive so that our data scientists can tweak or customize the AI models for different countries where the data sources, product SKUs, or cultural styles are all different. And also the pipeline for data processing, feature engineering, model training, and serving has to be very agile to enable rapid AI iteration and a time to market advantage. And finally, because of the global business expansion, it also requires a worldwide hosting infrastructure and a way to easily replicate the AI models, the services, and the entire framework across different countries in no time. So these are very unique challenges. Oh, press here. So as a proud partner of Microsoft, TaiCloud includes experts from industrial leaders like Google, world-class research institutes like Carnegie Mellon, and top 1% Kaggle contestants. We have been top contributors and community leaders for the two most popular projects on GitHub, that is Kubernetes and TensorFlow. We have also been a co-founder of a new open source project called Kubeflow that combines Kubernetes and TensorFlow to empower everyone with open AI capabilities. We have served multiple Fortune 500 enterprises through the combination of our container technology and deeper learning expertise. So coming back to the VIP challenge, we integrate with Azure, our container service called Compass, our AI engine called Clever, and AI modeling service called Cabernet to deliver a turnkey solution for VIP. So the solution includes a very flexible labeling system that can automatically tag items for over 1,000 customized labels. By leveraging the massive computing power from Azure, our AI engine can also achieve great velocity to enable rapid AI iteration. And thanks to the use of containers and container orchestration, we can deploy and replicate our services and solutions everywhere across the globe with Azure's presence. So this is an overview sketch of our integrated solution. So from bird's view, we can see our Compass is running on top of Azure to provide container microservice management. And our Clever and Cabernet further run on top of Compass to deliver a DevOps workflow for machine learning and AI models for VIP's needs. But what impressed me the most is the power, the openness, and the extensibility of Azure and Batch AI. For example, Azure fuels our products with its enormous computing power from CPUs, GPUs, storage, and networking at a global scale. And even though our AI pipeline Clever is very elastic due to the use of containers, Batch AI further boosts its performance and scalability via large-scale job management, auto-scaling, cluster management, distributed training, and inference. So beyond that, Batch AI also provides like well-defined APIs and SDKs, as Alex just mentioned, so that we can easily bring in our own solutions with very little changes on our side. And finally, Batch AI includes a wide array of curated AI tools like optimized TensorFlow, so we don't have to reinvent the wheel all by ourselves, but we can just assemble the entire solution from the given building blocks. So all of these coming together, we have achieved some amazing improvements and stunning numbers. So the overall efficiency has been improved by 85% after using this combination of technologies. And also on the training side, we have shortened the training time from 2 months to just 1 week. And on the inference side, the system can actually tag 1 million images with only 1% of the original processing time. So finally, I wanted to thank all the team members for the great collaboration across different organizations and across different time zones. Thank you. Thanks.
Thank you. So just a good example of a partner building on the Azure infrastructure, how we can help them through scale, be more efficient in their operations, and fit into their pipeline and tools. It's also a great example of one of these really interesting customer challenges that we were lucky to work with. We're happy to work with other people as well. We do hackfests around the world. If you have an interesting challenge that you think would be good engagement for the Azure engineering team, we'd be happy to work with you as well. We're mostly at the infrastructure level. We work with other data scientists, but we know how to make Azure shine. So the last area I want to talk about is what we call pleasingly parallel or embarrassingly parallel in the HPC world. It's really more about batch processing or automation in your work, not as much about experimentation, but again, I may have thousands of models to train and you do it in an automated way. How can I use infrastructure at scale to be more efficient, more cost-effective, better use of time in my work, and to share some ideas of where this can be used in a range of AI workloads. I'd like to show you one example of building many models. You may have in a factory tens or hundreds of devices, each with sensors. You can go and collect that data, and you want to figure out is something going wrong. So how can more of a classic machine learning case? How can I do anomaly detection on a stream of data? This demo was pretty interesting as well because it takes advantage of a number of services in Azure. We use event hubs to ingest that stream of telemetry. You can obviously use IoT as well, and prepare the data with stream analytics. I'm doing a very simple query here, but here's where you may do aggregation or time windows. We then store it in a SQL server, and then I have scripts that submit a number of training jobs. In this case, I'm going to run 15, 3 devices with 5 sensors each. The script goes and queries the database for the relevant data for that time window, does the training, and emits a model. And then use the same script to do prediction. Where parallelization helps is imagine I need to do 1,000 of these or tens of thousands of these. We do a lot of work with retail partners who want to build AI and ML models specific to every store or departments in the store. So it's not just one model. They want to train multiple models on a regular basis. They want to do this at scale in Azure just to save time, and they can build better and better stuff. So let me show you how this works. Here. So actually, let me start here if this is running. So here's just a little app that's creating a data point with a timestamp, device ID, tag ID, and that value. This is my simulated data that's being picked up by event hubs. You can see my event hub here that I've got about 60 messages per, I think I'm sending a message every second, so about 60 a minute. I've got a very simple query in Stream Insights that's basically taking each timestamp and sticking it in SQL Server. If I go over to SQL Server, I need to log in again. I can run a query, and let's just see how much data I have. So 36,000 records. So let's go down here, and we will go and submit a training job. So actually, before that, let me just show you the code that we're going to run. So this is my code to submit a job. It's using the Batch AI Python SDK. I have all the parameters for my job, the resource group, the cluster name, my credentials, the SQL Server in a configuration file. Kind of a best practice that we have. Don't put your secrets or configuration in the script. Once you start to productionize things, have them in a separate file. And then I pass in that configuration file what devices and sensors. Oh no. What devices and sensors I want to test. And I'm going to have to tell you the rest. That's bad. So it's going and doing and submitting a job for each device and each sensor. And going and creating the script is going and running a Python script on every node that goes and queries the database using the connection string that's passed in. Go and fetch the data. It's training with scikit-learn and creating an SVM model. Takes 30 seconds to train. I can go and then use that same approach to go and predict. So submit a job, instead of running the training script, run the prediction script, which is stored in Azure storage. So for each device and sensor, grab the training script, query the data, do the prediction. Any reading that then has a 1 is an indication of there's a potential anomaly. So this is a great example of a retail, of an IoT, of an industrial type of scenario where I'm going to be doing my work in Azure Machine Learning first to build those models, and how do I go and operationalize it at scale? This is not a web service. It's not pushing it out to a device. It's kind of more classic batch processing of, I need to run this model every day or every week on 10,000 stores. Do it for me in the most efficient way. Another example where we see a lot of batch processing is in the autonomous vehicle development workflow. This could be autonomous vehicles, forklifts, trucks, drones. It doesn't really matter, but there's a lot of stages and a lot of steps where parallel execution can really help. When I'm getting the data from the cars, I need to do what's called resimulation and get all the sensor data into a single stream. I may then go and tag the video data to find interesting scenes that I want to test. I'll go and then test that on my algorithms. Then I'll go and train and develop new ones, continue doing that testing. One problem that all of the autonomous vehicle developers have is they don't have enough data. I may be driving down the road and see some interesting scenes, but what about rain? What about snow? What about fog? So there's a big use of rendering here. So I can go and take a scene and then go and add in rain, add in different lighting. It's very common in retail too. If I'm going and taking cameras and scanning devices in the store, every store has different lighting, different angles. Products may be skewed. We're seeing a lot of use of simulation to go and generate training data. So I have another one of these, whether it's an HPC workflow, a batch workflow. I have to do a lot of computer work to generate more data that I can go and train on. And I'll be continuing to train and test. Autonomous driving is especially complicated because it's not just how is the car reacting. I have to understand how are the brake systems reacting. How is the body of the car handling that? What's the comfort? What's the safety? What's the skew? So there's actually a bunch of other simulation and testing of the sensors and actuators beyond just the logic of did I detect a vehicle or a person and did I stop? How much am I accelerating, and is the car designed right? So we're seeing a lot of integration back into the HPC simulation of how the car works. What is the, how does the body skew? And just a very interesting thing that what seems like a fairly straightforward, autonomous driving is actually a much more complicated thing. It speaks to all of the systems of the car, and is a very compute and very data intensive thing. This is also where we're seeing customers using all parts of Azure, right? People working with VMs, with Kubernetes, with Batch, with Batch AI, because everyone's bringing their own pipeline and tools. So it actually, in my view, speaks to the strength of Azure, is we're able to work with people where they are. We can go and help them accelerate and improve things over time, but we can also get anyone's workflow up and running very, 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 very quickly in the cloud. So when we think about doing this, it's more than just the AI workflow. There's a lot of around it, and a lot of pressure on the infrastructure. A couple of other tools you may want to look at that do kind of these pleasingly parallel or embarrassingly parallel things. We'll be rolling out later this year with Azure ML support for Dask. In the sensor demo that I was going to show, we had a script that goes and loops through, and for every sensor and device, go and run the script. I can do similar parallelization loops with Dask. So there I'm not doing it through a script, I'm doing it natively in Python or a language like Julia, and we're able here to leverage Batch AI as the compute infrastructure for that Dask parallel job. We've got a couple of other interesting packages that we have on Azure Batch right now that we're looking at. Does it make sense to bring them into Batch AI? Do Azure Parallel is a similar parallel backend for R. So for that for each loop, I can go and export it to a compute cluster. AZDK, or the Azure Distributed Engineering Toolkit, is a tool for Spark on demand. We have people say, I need to have like a Spark cluster for an hour to do my data processing and then tear it down. They may be using Databricks for their enterprise work, but they need just a give it to me now, run my job, and then turn it off. So we're able to build a Spark cluster on Batch. And then if you really want to work with the low-level part of Azure, I encourage you to take a look at Batch Shipyard and the Batch service itself. Shipyard is how we started the Batch AI project. It's a set of open source Python tools that builds a container-based workflow, mostly around HPC and AI on top of Batch. It's how we did our prototyping, the initial feedback of does the project make sense. The feedback was good, and we kept on hearing, this is great, I need a REST API and I need an SDK. So we effectively took the ideas of Shipyard and turned it into Batch AI and made it more of that enterprise class thing. So I hope you learned about some ideas about how you can turn that dial to full and get really speed up and performance when you need it in your apps, and some ideas around these different patterns of one job to multi GPUs, many jobs and many GPUs, and the other scale out patterns. And again, how you can come in Azure and work with VMs, work with one of the PaaS services, whether it's Batch AI or AKS or Databricks, and do your integration, or come in at the Azure Machine Learning level, which provides a great interface on top of all of these. So with Azure Machine Learning, you can leverage Batch AI, you can leverage a VM with the data science VM, you can leverage Databricks or AKS for scoring. Provides a very nice abstraction on top of the infrastructure if you're not developing specifically to one of those tools. Just a couple last point in terms of regions. Batch AI is in the US, Europe, Australia, and US government now. We will be in all GPU regions by the end of June. We can deploy in non-GPU regions as well, based upon demand, but I think the GPUs are in all of our major hubs. Here's a link to our documentation and our recipes. We're completing our preview now, and it will be GA later in the year. If you have questions or feedback and want to work with the team, you can reach us on the GitHub site or through the alias there. And that's all I have, so I encourage you to complete your evaluations. I can take some questions now, either on the microphone or in person. So we've got some time, so why don't we use the mic?
Hey, Alex, I think it's my second time hear your talk, but more content this time, thanks. So the Batch AI, I think, is a modern or a newer modern way of organizing or manage the GPU resources, right? So for similar systems, there are always same questions. So do you come with SLA? Do you guarantee the start time, completion time?
So we have an SLA around availability of the service. The provisioning time is a metric tracked by the Azure Compute Time, but not an SLA. And so the compute team takes very seriously the amount of time it takes for a deployment, competitiveness, as well as the success rate. So we track it very closely and have internal goals, but there is no SLA for provisioning in Azure.
Right. Another question is about the container support. Are you going to support the NVIDIA, what's it called, the GPU cloud containers, or going to integrate?
Yeah, so the question is, do we support the NVIDIA cloud containers? We have a sample or an example on GitHub of how to use it now. So we have a script of how do I pull, how do I pass the credentials to NVIDIA, how do I download the container and use it with batch. And you can put either the script in, you can put your credentials in the script or in Azure Key Vault. So again, you would either copy it down to every node. It actually scales fairly well, but better than GitHub, or you can copy it to Azure Container Registry. Any other questions? I'm also happy to stick around, so thank you.